Welcome back. In the preceding video, we talked about limits to infinity when we know what the horizontal asymptote is. However, not all graphs have horizontal asymptotes. Some have oblique or slanted asymptotes. So before we begin talking about our strategy when we're dealing with oblique asymptotes, let me ask you, let's find this limit as x approaches positive infinity of the function 1 over x. And so looking at this function right here, it's very easy for us to see that we have a horizontal asymptote. And the horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is going to be y equals 0. So that means the limit as x goes to positive infinity of 1 over x is 0, and also the limit as x goes to negative infinity of 1 over x would equal 0. All right, so rather than finding that every time, we're going to say, hey, this is just something that we know. All right, so we have two rules here. If we have 1 over x, that's going to equal 0. And an easier way for us to think about that, if I had 1 divided by infinity, how large would that number be? And again, infinity is not a quantifiable value, right? Infinity goes on forever. You think of the largest number you can always add 1 to that. But even if we thought about 1 over a million, if I had one candy bar and I had to share it with 1 million people, how much candy would I get? It would be very, very little, right? 1 divided into 1 million pieces is very, very small. And infinity, the concept of infinity, could be infinitely larger than that. And it's hard for me to use infinity and infinitely in the same definition, but that's just how big infinity is. So 1 divided by infinity is microscopic to the point where we just say, hey, that's going to equal 0. So we have a trick that we use when we're dealing with rational functions and finding limits to infinity. And this works for our horizontal asymptote examples that we did previously. It's just, why go the long way when you can take the short path? So what we will do is, this is our trick. We will divide every term by the highest power of x in the denominator. It must be in the denominator. Okay? So we can divide everything by the highest power of x in the denominator. And we can do that algebraically. If I had 1 over x, the highest power of x in the denominator would be x to the first. So I'd have 1 over x, right? And that's the same as if I multiplied by 1 over x and 1 over x. I'm just multiplying by 1. All right, so it's legal for me to divide every term by the same value because that's the same as like multiplying by 1. So let's look at an example. In this example, we're given the rational function f of x equals negative 3x to the fifth plus 4x squared divided by x cubed plus x. And we want to find the limit as this goes to infinity, or negative infinity in this situation. So what we do is we say, well, is there a horizontal asymptote? We're finding the limit of a rational function. Do we know where the horizontal asymptote may exist? And because the degree of the numerator is 5 and the degree of the denominator is 3, that means the numerator is greater than the denominator. And if the degree of the numerator is greater than the degree of the denominator, we have an oblique asymptote. So what we're going to choose to do is to divide everything by the highest power of x in the denominator. So I have x cubed and x to the first in the denominator. And 3 is bigger than 1. So I have 1, 2, 3, 4 terms here. And I'm going to divide each of these 4 terms by x cubed. And so this means I'm finding the limit as x goes to negative infinity of negative 3x to the 5th over x cubed plus 4x squared over x cubed divided by x cubed over x cubed plus x over x cubed. All right? So this is legal because essentially I just took this and multiplied by 1, right? 1 over x cubed divided by 1 over x cubed would be equal to 1. So I'm just multiplying by 1 to change this. All right, and I picked x cubed again because that was the highest power of x in my denominator. So let's look at simplifying this. The limit as x goes to negative infinity. This first term here, x to the 5th divided by x cubed, that is negative 3x squared plus 4x squared divided by x cubed. That 4 is still going to be over an x, so I have plus 4 over x over 1. X cubed over x cubed is 1, and x over x cubed is 1 over x squared. So at this point, if we looked at plugging in negative infinity, what would we get? So I'm going to take this negative infinity value here, and I'm going to plug that in for each of my x's. So this gives me negative 3 times negative infinity squared plus 4 over negative infinity over 1 plus 1 over negative infinity squared. And so what we know is that if I take 4 and divide it by infinity, 4 of something divided by infinity, large or small, is going to become so microscopic that it's going to approach 0. And 1 over negative infinity squared, that's 1 divided by, that's the same as 1 divided by positive infinity squared, because negative times a negative would be positive, and infinity squared is still infinitely large, so this is relatively the same as 1 over infinity. So this would also approach 0. And what I have here now is I have negative 3, negative infinity squared, that's positive infinity squared. So that's negative 3 times infinity squared over 1. And of course, I do not need to write divided by 1. So those two terms zeroed out. I just had 1 plus 0 in the denominator, which is dividing by 1. I don't have to write that. So negative 3 times infinity squared, that's just basically the same as saying negative 3 times infinity. Infinity squared is just infinitely larger. And a negative times infinity, this would simplify to negative infinity as our limit. And so if we were to look at the graph, if we were to take our original function that we started with up here and plug it in to our y equals. Here I've plugged this into my Desmos calculator, but we get a graph that looks something roughly like this. Now on the zoom standard, I'm zoomed way out here. There is a slight, it kind of goes like this up there. There's something subtle. It goes up to about +2, but we can't see that here because we are zoomed out to negative 20,000, all right? But in this graph, this is my function, and if we look at this, the limit as x approaches negative infinity of my function, as x becomes infinitely large in the negative direction, where do my y values tend to go? And the graph is going down forever, right? So as x becomes infinitely large, my y value is becoming negative infinity. And if we were to look at the limit as x went to positive infinity of this same function, if I'd evaluated it plugging in positive infinity, I also would get, as x becomes infinitely large, as x goes to the right forever, my y values are still going down forever. We would get negative infinity. So I hope that helps. I'm going to do one more of these problems in a following video.